The Fibonacci sequence and mathematical modeling in nature. A merchant's son changed the way numbers were written. Instead of Roman numerals, he brought new numbers that made calculations much easier. In a world where people traded goods and carefully kept records every day, he knew from experience how inconvenient the old numbers were. Through a book called Liber Abaci, he introduced the Hindu-Arabic number system to Europe. We call him Fibonacci. The book explains how to calculate with the new numbers, shows how useful they are in trade, and later presents many interesting math problems. From one problem in the book, an unexpected sequence was born. It all started with a single pair of rabbits. On a farm, there lived one pair of grown rabbits. Each month, they had one new pair of bunnies. After 2 months, each new pair of bunnies also began having one pair of bunnies every month. Let us assume that none of the rabbits ever die. In the first month, there was one pair of rabbits. In the second month, there were 2 pairs. In the third month, 3 pairs. In the fourth month, 5 pairs. The sequence went like this: 1, 2, 3, 5, 8, 13, 21. The rule of this sequence is that each number is made by adding the 2 numbers before it. Today, we call this sequence the Fibonacci sequence. This simple rule does not stay on the farm. It appears in nature too. In a honeybee colony, only the queen lays eggs. She lays fertilized eggs and unfertilized eggs. Fertilized eggs grow into female bees, and unfertilized eggs grow into male bees. Female bees have 2 parents, but male bees have only a mother. Now, shall we trace the family tree of a male bee? A male bee has 1 mother, but he has 2 grandparents. This is because his mother, the queen, was born from a fertilized egg. So when we trace back the number of his ancestors, 1, 2, 3, 5, 8, the Fibonacci sequence appears. Nature does not calculate, but it leaves structures behind. We write those structures down as numbers, and we look for the rule that creates them. Then we see if the same rules work in other places. If we count the flower petals, look at the arrangement of sunflower seeds, or count the scales on a pine cone, we often find Fibonacci numbers. Why do you think that is? To survive, plants try to use light, air, and space as efficiently as possible. Their leaves are arranged so they do not cast shadows on one another, and their seeds are packed closely to leave very little empty space. Flower petals work the same way. Before a flower fully blooms, the petals form a bud to protect the delicate parts inside. When the number of petals is close to a Fibonacci number, the petals fit together more tightly, leaving fewer gaps, and the flower holds a more stable balance. The sequence is simple, but the structures it creates are remarkably precise. The Fibonacci sequence now appears in art, architecture, and music. It is even used in efforts to explain changes in the stock market, such as the Elliott wave theory. Of course, not every change can be explained by this sequence. The Fibonacci sequence is not a code that decides our destiny. Yet we often see similar rhythms repeat in nature, in living things, and in human behavior. This leaves us with a question. Is the world we see around us truly as complicated as it seems? Or could simple rules have layered together to form the motifs we see? The sequence does not demand an answer. It simply helps reveal the invisible structures that were there all along.